I am happy to have Automotive Seminars as a sponsor for the show. Now, if you're not familiar, Automotive Seminars is a diagnostic technician training company. They've got a website that there'll be a link to in the show notes. And what they offer is top-notch training to technicians like us in the field. I've been taking their training courses for years and have got a ton of benefit out of it. They've got top-notch instructors, John Thornton, Scott Shotton, Scott Manna, and every other month they've got a 2-night course that you can sign up for. Join in, ask questions, and afterwards, you've paid for the course, you can access a recorded version whenever you want. You can rewatch the class 2 years later in case you wanted some details on it. And that is a fantastic feature. So make sure to check out the website to see what courses they have available and what's coming up in the future. This podcast is brought to you by Jarhead Diagnostics. Jarhead Diagnostics manufactures in-house diagnostic equipment and storage solutions, as well as distributes for companies like Pico, ATS, and TopDon. One of my favorite tools that I've bought from Brandon and Jarhead Diag is the case for the U-Scope. If you don't have a U-Scope, you probably should, but if you have one, you got to get one of these 3D printed cases, has a magnet on it, has a full-size BNC lead that you can connect to, and it gets rid of the weak point of that scope, which is the mini BNC connection, which is pretty fragile. This case makes this thing nice and secure and makes it an even better tool than it was. So check out jarheaddiag.com. The link is in the show notes. This episode is brought to you by L1 Automotive Training and Keith Perkins. If you're looking for education on module programming, J2534, EEPROM work, key and immobilizer, electrical diagnostics, or drivability diagnostics, Keith has a website, l1training.com, that's got over 60 hours of training videos on all those subjects and more. When I first started out doing mobile, I utilized Keith's videos on module programming in J2534 in order to get my head wrapped around what I would need for the tooling, the computers, the software setups, what kind of obstacles I would be up against when I'm out there programming modules on cars. And it was a huge benefit to me. And I continue to use the training videos that he has on his website. So I strongly recommend checking out l1training.com. We have got Auto Rescue Tools and Isaac Rodell as a sponsor for this podcast. Hey guys, if you're looking for programming laptops, you want the laptop set up ready to go for programming control modules on vehicles, you need key cutting equipment, you need diagnostic tools, Isaac is your guy. Has all that stuff available for purchase, and the support that he offers along with the purchase has been outstanding. I bought some stuff from him in the past. I got my Dolphin key cutting tool from him several years back. And again, the support has been phenomenal. Helped me out along the way with anything additional I needed to make it work for me. Also, for the month of June 2023, they've got Autel updates for sale. So make sure to check that out as well. Again, that's autorescuetools.com. The link will be in the show notes. Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping, and you are stuck with just me today. I'm going to be covering another request that I had through the Facebook group, which I appreciate. Keep those coming. I'll do as many as I can. This one's going to be variable valve timing. This is a system that's been on vehicles for quite a while. Really nothing new.
seen this since the 90s on a lot of vehicles. But it can be tricky to diagnose in some cases, depending on the problem and the component that's at fault. So what I'm going to do is I'll give you a real brief overview of how variable valve timing works. Most of you probably have a pretty good understanding of the system. And then I'm going to go through 3 different vehicles that I diagnose problems with relating to the variable valve timing system, and through those explain the components, the testing procedures, some of the faults that we can see, scan tool data, and tools that we can use to determine what's wrong. So with that said, I'll jump into the brief description here. I won't spend too much time on this, but what is VVT, or variable valve timing? This is basically just when we're changing the position of the camshaft in relation to the crankshaft while the engine is running. Okay. So engine's running, we get to a certain engine load or engine RPM, and we're actually going to shift that camshaft so that it opens and closes the valves, intake or exhaust, or both potentially. It's going to change when those open in relationship to the crankshaft. So at idle or low loads, we can have those valves open in a certain way. And then under a larger load or under acceleration, we can change that valve opening. And we can do this for a few different reasons too. This can be done in order to achieve better emissions for an engine, right? We've seen EGR pretty much be removed from gasoline engines in most cases, thanks to variable valve timing, because we can actually close that exhaust valve a little bit earlier than we normally would to trap exhaust gases in the cylinder. And that creates our EGR effect rather than piping it back in, through an intake, through some tubes, and having a valve and lines that can plug up and valves that can fail. Now we just leave the exhaust gas in the cylinder, right? That would be an emissions application for variable valve timing. And of course, we can change the engine breathing. Again, we can get that valve overlap effect to help with engine breathing at a higher engine load, kind of like having a performance cam. You hear a muscle car that idles really poorly is essentially what it is, but it gives you that lopey cam sound, which does sound cool, but on a regular everyday driver, we don't want that at idle. It's not going to be efficient, or the engine's just not going to run well at low RPMs or low loads. But that camshaft, that fixed camshaft in the muscle car, is designed to give it better engine breathing and better performance at a high engine load, a high engine RPM, as the air is moving through the engine a lot faster. That valve overlap helps the airflow through the cylinder to fill the cylinder more completely as it's running. Anyways, we can get a couple different things out of this, and that's the idea behind variable valve timing, is we're essentially changing the camshaft as the vehicle's running. Okay, now we can add other things in there like variable intake runners and variable valve lift. Those are other systems, and we can really increase the performance and the engine breathing aspects. But variable valve timing is changing when the camshaft is opening the valves in relation to the crankshaft. That's it. And we do it mid-engine operation. We actually switch the position of that camshaft independently from the crankshaft. So in order to do this, we have phasers, or actuators is the other name, or sprockets. And I'll probably refer to them mostly as phasers, but this is the component that is bolted to the camshaft that actually allows the camshaft to shift position. And we're going to do this through oil pressure in pretty much every situation that I've worked on. I think I've read about electric motor phasers, but I've never actually worked on one, so I can't really speak to that. But we're going to use oil pressure fed into these phasers at a particular time, controlled by a solenoid that is controlled by the ECM, engine control module. And it's going to regulate oil pressure into these phasers, which will hydraulically move the camshaft to one position or another, again, as the engine's running. Of course, we need oil pressure from the running engine in order to do this. Now, some of these phasers are a vane style. I'd say that's probably the most popular one. Some of the older ones were a helical design, were actually spun in side of the phaser and move the camshaft to a different position. I haven't seen those on newer vehicles, but like the old Trailblazers had them. I actually just dealt with a Lexus, an older one, is 2002, that had a helical style phaser, and it was actually timing belt driven, which we don't see too often. Usually the phasers are going to be chain driven and submerged in oil, but this one was a timing belt driven phaser, and the phaser itself was leaking oil. You could take these things apart, and there's a big O-ring, and you can take basically the outer portion of this helical gear off, replace the O-ring, fix that oil leak. But anyways, there's different styles of phasers, but really it's all to accomplish the same thing, is to move that camshaft to a different point in its rotation than where the crankshaft is. So if you think about the timing belt or the timing chain, it's going to stay fixed in a position to the sprocket that it's driving on the camshaft, but the actual camshaft can move within a certain range. There's a limit to how far it can move, either advanced or retarded, but it will allow that camshaft to move, again, while the engine's spinning. So that's the goal of the system, and that's how we accomplish it. ECM controls a solenoid of some sort that is going to control a phaser that is going to move the camshaft. And that's what's involved. A couple other components that we'll bring up through these case studies, but that's the basics. Now, before we get into this, obviously we can have a number of problems with these systems. Different things can fail, but the number one thing that you want to remember and check first before you dive into anything that would be considered advanced or time-consuming for diagnosis is check your oil on these things. And I'm sure you're well aware of this, but I just want to make that really clear before I get into this. And I'll mention that I checked the oil on all these vehicles that I'm working on. If you don't have the proper level, if you don't have the proper viscosity, if you don't have the proper quality of oil, if it's really dirty, it's black, if you don't have oil pressure in general, right? You could have a full oil system but still have low oil pressure. This system is not going to work. It relies, regardless of the vehicle, it's going to rely on adequate oil pressure. Not only oil pressure for the engine, but oil pressure to the phaser itself. If it does not have that, this system will not work. So we need to verify our base engine oil pressure, oil level, oil viscosity before we dive into any advanced diagnostics on this system. So check that, make sure your oil is in good condition. If it's not, if there's any question, change your oil, get a fresh oil change in there, and verify that it's the correct oil for that engine. Now, checking viscosity isn't the easiest thing to do just by looking at the dipstick, but we can question the customer, right? When was the last time that you had your oil change? Did this problem that you're having appear after your last oil change? Maybe somebody put the incorrect oil viscosity in there. It's possible. Of course, if it's low or dirty, I think we can figure that out pretty easily, but just get that out of the way. Make sure that that is not causing your problem for this VVT system before you dive into any of these other things. And there can even be problems, after an oil change with filters. I've seen that too. BMW is a really good example. A number of them, it has like the paper cartridge style filter where you take the big plastic cap off the top of the engine, and there's a plastic cage in the middle of the filter that goes down, has an O-ring at the bottom, and you can actually remove this cage from the cap that holds the filter in place. And sometimes people will do an oil change on one of these, they'll rip the filter out and they take the cage with it, not realizing that that cage needs to stay in there. And they put it back together. You can put the filter in, you can screw the cap back on. Oil pressure for the vehicle will be fine, but the Vanos or VVT, that's BMW's name for VVT, will not function properly, and you get codes for it. Well, you have to replace that cage that goes in the middle of the filter. So again, just another example of, we want to see, did this problem occur after you had the oil serviced on the vehicle? Because that does happen, and we just, again, want to eliminate that as a potential problem. So going with the theme of oil pressure, that'll be my first case study here. And this was a vehicle I actually looked at several years back. I was working at Firestone as a technician at the time. It was a 2006 Toyota Tacoma with a 4.0 liter. This is a overhead cam V6, and the intake cams on both heads are going to be phased, meaning that the exhaust cams are not phased, they're fixed cams, but the intake cams are phased. They have actuators and they have solenoids, one for bank 1, one for bank 2. Now, some vehicles can have both exhaust and intake phased. Some of them can just have the exhaust, Trailblazer being one of those. And a lot of them will just have the intake phased. And the code that this vehicle came in for was a P0022, which is camshaft position A, timing over retarded. If you see camshaft position or camshaft A or B referenced in your service information or your scan tool, just remember, as far as I've always seen it, A is going to reference intake and B is going to reference exhaust cam. Okay, so this is A, meaning that is the intake cam. And again, those are the ones that are phased on this vehicle. Now, some of these earlier systems, I realize this is a 2006, didn't do the best at separating variable valve timing problems from actual base timing problems, meaning that if the timing chain on this vehicle had just jumped and we're a couple teeth out, the engine computer might not be able to differentiate between, hey, we're just out of time, or we're out of time all of the time, or that the only time that it's out of time as far as valve timing goes when we're trying to activate the VVT, right? Newer vehicles, you'll see a difference between these codes. You'll see codes that pertain specifically to VVT, and then you'll see codes that specifically correlate to camshaft, crankshaft correlation. Some of these are earlier vehicles, there wasn't much of a difference when it came to the codes. And even on some newer stuff, there isn't. But I just wanted to point that out because this code, this P022 says camshaft position A, timing over retarded. Now that could just be that this vehicle is out of time. The timing chain jumped, right? But it could also mean that the camshaft is not moving to the position that it wants it to when it's attempting to phase it. So me as a technician, I have to determine what is actually happening here, what's causing this code to set. Now, if you go through the information on the code, which I always like to do, I always like to read at least through the flowchart of the code, maybe not follow it exactly, but I like to read through it. It does bring up VVT as a potential issue for this code. So of course it's on our minds and we need to be aware anytime we have a timing code for an engine, let's consider the VVT system, because if the VVT system has a malfunction, it's moving that camshaft, which is where the cam sensor is going to read off of, is the actual camshaft position. And that could cause a timing code, right? Because essentially at that point, if the camshaft moves and the computer didn't command it to do so, well, essentially we are out of time. But it may not mean that the timing chain itself has jumped. It just means that the VVT system is activated when it doesn't want to. But the basics for this code, again, are that the bank 2, which is on the driver's side of the vehicle here, the bank 2 intake cam is not in the position that the PCM expects it to be in. That's the basics of this code when you read out the definition. So my goal, and again, it lays this out in the code criteria, is to determine if the timing is off all of the time or if the VVT system has failed. That's the difference that I have to make as a technician to decide which direction I'm going to go. Now, there are a couple clues here that lead me to actually go after the variable valve timing instead of the base engine timing. Number one, the engine runs really well at idle. Now, it could still be off maybe a tooth or so. That's definitely a possibility. And I don't want to just use that as my only piece of evidence, but it does seem to run very well at idle, indicating to me that the base timing is probably okay. Now, here's the other one that's kind of a big giveaway, is that the code sets only when the engine is revved up or you drive it, meaning that the VVT is activated, okay? Now, and this is something to bring up, is that most vehicles will not activate the VVT system until you get it to an elevated RPM. That's not true of everything, though, and we want to be vigilant of that because there are vehicles that phase the cams at idle. That is definitely a thing out there. Traditionally, when we go back to older vehicles like this 2006, it wasn't very common. Most vehicles would only phase as you elevated the RPM. Okay, but do keep in mind that some will phase at idle, and we're going to have to use our scan tool to determine, is this thing even attempting to phase the cam? But this particular Toyota, it would only phase and would only activate the VVT system if you elevated it off idle. If you put it under a load, you went out and drove it. And my code would only set, if I cleared that code out, it would not set if I just let the engine idle. And it even says in the code enable criteria that it monitors for this code anywhere between 500 and 4,000 RPM, right? So my thought process here is if my base timing was off, if the chain had jumped, that I should set this code at an idle based off of what the code criteria says, but I can only get it to happen once I rev up the engine, leading me to believe that the VVT system is not functioning the way it's supposed to on bank 2 intake cam. So now I can go after the VVT and try to determine what's going on here. So my first step here is going to be to run an active test on the VVT system. And this is a big one for any system that has VVT and the solenoid operated phaser is we want to activate it somehow or another and see, is it actually working? How do we do that? There's a number of ways that you can do that. Of course, like I mentioned, you can rev up the engine and look for some different things to see, did this actually activate? We can look at data PIDs in the scan tool and see a lot of times you'll have a desired and actual data PID as far as the camshaft position. This particular Toyota did not have that in the data stream. We can, in some cases, run a bidirectional control with the scan tool and activate these solenoids. And these solenoids are going to send oil pressure to the phaser, unlock the phaser, and move the camshaft. And if we do that at idle on this particular vehicle, if I activate the solenoid with the scan tool, which I can with this one, I can activate the solenoid and get the cam to phase. If I do this at idle, I should expect the engine to start to run rough. And again, it even lays this out in Toyota service information. This is a test they want you to run, and that's their verification, is turn on the VVT solenoid using the scan tool at idle when normally it would not be activated. You should shift that camshaft to its advanced position, and the engine should run rough because it's not meant to have that advanced cam position until you're at a elevated RPM or engine load. It's kind of like our old school EGR test, right? If we want to verify the EGR has flow, we activate it at idle, and the engine should run rough and stumble, right? And we're not pumping in exhaust gas in this case, but we're changing the position of the camshaft. We're changing the valve position. We're essentially putting the engine out of mechanical timing for a short period of time, but we expect it to happen that way. That is our expected result if the system is working correctly. Okay, so let's do this. Let's grab our scan tool. Let's activate the solenoid using the bidirectional controls. So I do this. I hit the button on bank 2, and nothing happens. Right, the engine does not change the way it's idling at all. Idles smooth, has no issues. Okay, so that's a problem. But I always question, especially with the aftermarket scan tool. I think I was using an Autel on this one. Even though the functions in the scan tool, maybe it doesn't actually work with this vehicle. I've run into that plenty of times. So I tried it on bank 1, right? Because I don't have a code for bank 1, but I'm going to give it a shot over there. And I activate bank 1, and the engine actually does idle rough. It stalls, right? Or I don't know if it actually stalled, but it came pretty close to it. So I know that the scan tool has the capability of activating the system, and I can see on bank 1 I have my expected result. But on bank 2, I don't seem to have anything at all. Does not activate at all. So this is also going to confirm what I was thinking, that it's VVT system related, and this is why the code's setting, right? And when I go to rev up the engine, the computer's trying to do the same thing. Now, the computer is going to be looking at the cam and crank sensors to determine if the cam actually phased, but I'm looking at just how the engine's running, and I'm seeing that there's no change. The computer's seeing there's no change, so I understand why it's set in the code. So now my goal is to figure out why that system is not activating. What are some of the possibilities? Of course, we could have a solenoid that's failed. We could have, the wires to the solenoid that's failed. Maybe an ECM problem, that's unlikely. Or we could have a phaser issue as well, right? The phaser's just not physically moving. It's stuck in place, something like that. Okay. So where do we start with this? First things first, I'm just going to check and see, is the computer getting power and ground to that solenoid? And odds are I'm going to be doing some testing at that solenoid anyway, so might as well get to it. And it's right in front, pretty accessible, not too hard to get to on this vehicle. So I hook up to the 2 wires, it's just power and ground to the solenoid, and I verify that I am getting power and ground to the solenoid when I activate it with a scan tool. So I hit the button, my test light lights up. Okay, cool. That's all I wanted to see. So I know the computer has the capability of moving this thing, but it's not happening. Okay. So next thing I did was I actually removed the solenoid from the cylinder head, and I just want to see, can I physically move this solenoid, right? So I know it's getting power and ground. Let's see if the solenoid has failed itself, because that happens all the time. These solenoids go bad. If you work on GM Ecotech engines, you probably changed hundreds of these things. Very common to see these things fail. And so I send power and ground right to the solenoid, and it does move. It actually opens and closes the way I would expect it to. Now, this is out of the vehicle, and I was considering this, and I didn't really pursue this much more. Again, this was quite a while ago when I was working at Firestone on flat rate, and you just got to keep things moving along and this flat rate mindset. So I told him, I was like, you know what, just order me a solenoid just in case. I want to verify that, you know, this is not my problem. I didn't really go too in depth beyond just checking those things. So kind of shotgunning apart here, but the other thing that you could potentially do on a vehicle is swap the solenoids from side to side. These ones, the mounting position for the bracket, you weren't able to do that between bank 1 and bank 2. So anyways, I had them order me a solenoid. So I get a new solenoid, even though that one was moving. I just wanted to verify that's not what's going on. Pop the solenoid in there, and it's exact same. Okay. And, you know, some of my thought process here was to, if it's not the solenoid, it's probably going to be in the phaser. And the phaser is pretty tough to get to on this. You got to pull the valve cover to access it, and probably the timing cover as well if you actually want to replace it. And that could be really challenging, you know, just to diagnose, and then maybe the customer doesn't want to fix it, right? But anyways, I replace the solenoid and get the exact same result. So I can pretty much verify that my solenoid was not the problem. It was activating the way it's supposed to. My computer is commanding it to turn on. So what is left here? What else am I after? Is it just the phaser? Now, I mentioned before that I at least went through the flow chart for this code, and I try to make a habit of doing that for any DTC when I'm looking through the information, is at least scan through the flow chart. You don't have to follow it step by step. And I wouldn't really recommend that in a lot of cases, specifically because in this flow chart, it has you check the base timing for this engine, meaning that you're pulling the valve cover and look at the timing chain before you even check the solenoid for this code. That's how the flow chart goes. And that's not really my approach. That's not how I would do it. I would leave that timing until maybe one of my later steps, or kind of eliminate it as a possibility like I did, meaning that it idles just fine and the code does not set until I rev the engine up. So I know this is VVT related, so I'm not pulling valve covers and stuff just yet. But going back to this flow chart, if you go down the list, so number 6 step says to check the VVT filter. Okay. Now, it really hadn't mentioned anything about this prior to this, and you actually can't find a whole lot of information on this filter anywhere else besides in this code flow chart. So I'm asking myself, what is this filter? What are we talking about here? Now, I've seen other VVT solenoids that have filter screens on them. These particular solenoid did not. So my question is, okay, maybe there's a remote filter, and I've seen these before, that filters the oil before it gets to the phaser, well, before it gets to the solenoid, and of course, before it gets to the phaser. It's just a little metal screen. Now, it's not on the solenoid, so maybe it is remote. So I do some digging, and finally, where I find this in the service information, now I am using aftermarket service info, so maybe factory Toyota information will have this laid out a little better, but the only other place that I found this was in an exploded view of the cylinder head. And on the outer portion of the cylinder head, towards the bottom of the head on the front, there is basically what looks like a bolt, but it's a plug. And if you remove this plug, you can take a little round screen out of the cylinder head. And this is on each side of the engine. This is the remote filter for the VVT system. So oil pressure gets pumped up into the head, goes through this screen up to the solenoid, and once the solenoid activates, to the phaser to phase the cam, right? So if this screen is plugged up, we'll never get oil up there. And it lists out in the code, hey, you should check this before you finish the diagnosis to make sure that that is not your problem, right? And this goes back to originally what I was talking about. Oil pressure needs to be present or these systems will not work. The phaser could be in perfectly good condition. The timing could be on. The solenoid could be moving physically. And we still might not have operation if there's no oil pressure, which was the case here. I removed that plug. I removed the screen. It was completely plugged up with just dirt, carbon, whatever it is, what you'd expect to see in an engine, a high mileage. And so it was as simple as cleaning the screen up. Now I did pull the other side, and the other side, even though that was working, did have some restriction on it. It just wasn't as plugged up as the failed side. So I cleaned up both of these with some brake clean and some compressed air, popped them back in. As soon as I did that, it was back to normal. Both sides were phasing the way that they were supposed to. You could activate it with a scan tool. You could drive the vehicle. It didn't set the code. We're fixed. So pretty straightforward and simple once you know that that filter screen is there and to check for it. Now, does every vehicle have a remote filter screen? No. I would say the majority of them are going to filter out through the solenoid and screens built into the solenoid, but that's not the case for everything. There are plenty of these that have remote screens, and so it'd be worthwhile, if you're having an issue, to check to see, does the vehicle I'm working on have a remote screen, and should I check that to see if it's plugged up or not? So that's my first case study. Remember that we need oil pressure to the phaser in order for it to work, and there are various reasons why that might not happen. So the next vehicle is a little older as well. It's actually the same year. It's a 2006, so I don't mean to be giving you case studies on old stuff that you're not going to see, but I thought this one was actually pretty interesting as far as what the solution was and why it was acting the way that it was. So this is a 2006 Nissan Sentra, and this is a 1.8 liter 4-cylinder engine. This is setting a P0011, and the shop has actually replaced the timing chain on this vehicle as well as the VVT solenoid twice. So they put 2 VVT solenoids on there. They replaced the timing chain. This is a pretty competent shop as far as the mechanical repairs go. So I was fairly confident that they knew what they were doing as far as replacing the chain, but they're still getting this P0011. The definition for this code is intake valve timing control performance. Okay. So on this engine, much like the Toyota that we were talking about, the intake cam only is phased, even though it is a dual overhead cam, has a cam for the exhaust. The intake only is phased, has one solenoid that activates the phaser for this intake cam. And of course, we're getting a code that seems to pertain to that system. So what is my problem here? How do I want to approach this? Do I have a phaser issue potentially? Maybe there still is a timing issue. Just because I trust what these guys do doesn't necessarily mean that there's not a timing issue. I can't rule that out. Solenoid issue still, maybe, failed parts. It's definitely possible. You get 2-3 bad parts. Maybe a computer or circuit issue. Any of those are possible, maybe something else, but I want to try to understand the code, understand the system, and then I can go through and start checking stuff. So first off, let's check the oil. And I did do that on the Toyota as well. Make sure the oil is full and clean. And both of these vehicles, oil level was full and clean. And they had changed the oil just to be sure on this one as well. So that was not a concern of mine. And actually, if you go through the flow chart on this one, the very first thing that Nissan tells you to look for is to see if the oil pressure light is on the dash. And if the oil pressure light's on the dash, you're supposed to stop and resolve that first, obviously, before you chase this VVT code. But again, good reminder to everybody, we've got to have adequate oil pressure before we proceed in the diagnosis of these codes. Now, I'm not the biggest fan of Nissan service information. Maybe you are, but I've not always been a big fan of what they have out there. And they don't give you a whole lot of information on this code as far as when it sets. There's a few details that I'll go over, and there's a flow chart at least. But as far as like enable criteria and stuff like that, they're not real precise in what they're offering you. The data PIDs are somewhat limited to, they give you the duty cycle of the solenoid, so what the computer is at least attempting to pulse the solenoid at for a percentage. And then there is a intake valve position, but there's no desired data PID, right? So when I look at scan tool data PIDs for VVT, I want to see desired position of the camshaft, actual position of the camshaft, and sometimes they'll even give you a variance between the two. So you don't even have to do the math. You just look at the variance, you want that at 0, meaning the difference between the actual and the desired, they should match, right? If the computer wants it at 30 degrees, as far as the phase angle, the actual should say 30 degrees measured by the cam and crank sensors. It doesn't have it in this one. There's just an actual position and then there's a duty cycle. So really through the data PIDs, I could tell when the computer is attempting to phase the cam. And I guess I could probably tell if the cam is moving, if it phased at all, but is it in the right place? Pretty tough to tell just from the data PIDs on this. So I'm limited. Again, this is an older vehicle. The newer ones are usually a little bit better as far as the data PIDs go. Also, the other thing with this is I don't have a bidirectional control for this vehicle in order to activate that solenoid. So what I decided to do with this one is I wanted to clear the code because they said it was very consistent in how it sets, but I want to see exactly when does this set. Now, this actually was just like the Toyota that I dealt with. The code would not set in an idle, but it would set once I revved up the engine. Meaning once it attempted to phase the engine, that's when the code would set. So I'm going to approach this much like I did the Toyota here. I'm wondering, is the VVT system just not activating for whatever reason? And I want to activate that solenoid. Now on this Nissan, I had to manually power and ground the solenoid because I didn't have a bidirectional control. So I do that. I just touch power and ground. And you want to be careful if you do this. Number one, don't send power and ground to the wrong circuits and damage the computer. But also, even if you disconnect the solenoid and just jump power and ground right to it, don't do it for a long period of time. And they actually lay it out in the service info too, no longer than 5 seconds, or you could damage the coil and the solenoid. They're meant to be pulse width modulated, not straight power and ground all the time. But we can quickly touch power and ground to it, activate that solenoid. I did that, and I expect the cam to phase. Now I'm doing this at idle when normally on this engine, it does not. And I expect the engine to run rough, right? That's the same test on the Toyota. Now, in this case, it does happen, right? The engine runs rough. You can tell that that camshaft changed positions. So I know my solenoid works, which is brand new. And now I know that my phaser works. So this is a little different than the Toyota. Of course, my question is now, is power and ground actually getting to the solenoid from the computer? So that's my next test here. Okay, maybe there's a circuit issue causing this solenoid to not activate because it's not getting power and ground. Well, I checked that and it is. Now, I will note here, as long as the code was set, the computer would not attempt to phase it. You'd have to clear the code and then rev up the engine. And after its first attempt, it would set the code and it would stop. But you could see, okay, it's getting power and ground to this phaser. But for some reason, this code is setting as soon as it attempts to phase the cam. It's not liking what happens once it attempts to. So I'm also getting a little bit of the code strategy just by doing some testing, as I know when the computer is looking for this is once we rev up the engine. Once it's attempting to phase, it's looking to see, did the cam go to where I want it to? And it must not be. Or something's going on where the computer's determines something's not happening the way I wanted it to. So what's my next step here? Do I want to look at base timing? Is that a potential? I mean, I would expect there to be code setting at an idle, but I'm not 100%. Is it an issue where, for whatever reason, manually jumping this thing, I can get it to phase, but when the engine revs up normally, it's not? That's a potential. I want to verify that this thing is actually phasing, or is there something else going on? And I did, again, glance through the flow chart, and it does list things that you definitely want to consider, or at least check as you're going through the diagnosis. Now, a couple of those things in this flow chart that has you check early on in the steps, Before you even check base timing is the cam and the crank sensors to make sure that those are outputting correctly. And that's a point that I wanted to make about the VVT systems is the components that we're using or the ECM is using to monitor this system for proper operation is the cam and crank sensors, right? We're looking at the crank sensor and then we're looking at the cam sensor to see, are we in time? Do the cam pulses line up with the crank pulses where we expect them to? And then if I phase it, does the cam move to a different position? Looking at the cam sensor, right? So we have to consider that if these sensors are not working properly, the VVT system may not be working properly. And again, lays it out in the code criteria or the code flow chart for you is to verify the operation of these sensors. So I decided to kind of tackle all this as one. And what I'm going to do here is I'm going to scope the cam and crank, and there's only one cam sensor, and then there's a crank sensor. So I'll be able to look at the signal quality out of these sensors. I'll be able to compare the base timing to a known good, hopefully, if I can find a known good. And I can phase the cam, I can activate it and see, am I actually moving as far as the camshaft position goes? So I can tackle a lot of stuff here with one test. So I hook up to it, I get my idle reading, I rev up the engine with the codes cleared. Of course, the code does set, and then I have my waveform. So again, what I'm looking at is signal quality from the cam and crank. I'm looking at base timing to see if we're aligned. Base time, the actual chain timing is good. And then I'm seeing, does the camshaft position move when I rev up the engine and my duty cycle goes up? So I look at all that, and the patterns seem to be pretty good at first glance. A nice square wave on both the crank sensor and the cam sensor. And I'll actually put these pictures in the Facebook group so you can see what I'm talking about. But first glance, this looks great. I don't see any issues with it, but I do want to compare this to a known good. And so I actually ended up finding one on IATN for this one. Same vehicle, same engine, same year. And I compare it to mine, and at first glance, again, they look very similar. And what I started to do was to line up the cam position with the crank position on the Pico. You can use the rulers and the cursors in order to line stuff up because I'm looking at base engine timing here. But while I'm doing that, while I'm comparing it to my known good, I noticed something about the cam sensor. My cam sensor, the pattern, although the teeth are in the correct position, right? They're lined up in the same spot in correlation to the crank as my known good, the pattern is upside down. Meaning that on my known good waveform that I got off of ITN, the pulses start at 0 and go up in voltage. So if you imagine a square wave going up from 0 as the tooth goes past it, and then down back to 0 as it moves past the tooth, mine's the opposite. My voltage starts high and drops down when there is a tooth. So if you were to put the two patterns right next to each other, they're like a mirror image. They're inverted from one another. It'd be looking at a CAN bus waveform, right? CAN high and CAN low. It's the same pattern, but it's inverted. One goes high, one goes low, and that shouldn't be the case. And so I actually did a little bit of digging. I found another known good just in case, and it was the same as my first known good, where the voltage went up from 0 when a tooth went past it on the camshaft sensor. But mine was going from high to low. Now, again, the teeth lined up exactly where they should be, meaning that my base timing is okay, but my cam sensor is putting out an inverted signal. And I verified power and ground of the sensor. I verified my scope connections to make sure I wasn't doing something incorrect. But that was the case. This had an inverted pattern coming out of it. So I told the shop, get a cam sensor, put it in here, we'll see what happens. And they did that. And I was still at the shop at the time. And we fired it up, we revved it up, we drove it around, did not set this code anymore. It was fine after this. Engine was in time, cam was phasing the way it was supposed to. So why did this code set? Well, the computer is going to be looking at the falling edge of the waveform to determine the tooth position. And again, take a look at the pictures in the Facebook group and it'll make a little bit more sense. But if you're looking at falling edges and the pattern is inverted, it basically moves the teeth to the wrong position in reference to the crankshaft. as to what the computer expects, because that's all the computer's looking at is a falling edge on that camshaft waveform. But now those falling edges are in a different spot, even though the teeth physically are not in a different spot. So something internal on that Hall effect sensor had gotten screwed up and it was putting out an inverted waveform. So replacing the cam sensor fixed it. The other question I had was, well, wouldn't that have set a base timing code, right? That should have been a problem for the ECM at all points. Well, after some investigation, I looked through all of the potential codes for this vehicle. It does not have a base timing correlation code even available to set. Now, most new vehicles are going to have this. This one didn't. That P0011 was pretty much the only code that could set in reference to engine timing. And of course, it involved the VVT system as well. But this is a pretty early system, pretty basic, and that was all that was available as far as a monitor goes on this system. And it did flag it. But that was the fix, was an inverted cam sensor. So that was kind of an oddball one. You don't see that too often, but it points out the fact that we need to observe our cam and crank sensors to make sure that these systems are operating properly. All right, my final vehicle here is going to be a 2013 Infiniti QX56. Okay, this is a 5.6 liter V8. This engine has VVT and VVL, which is variable valve lift, big motors on the top of the valve cover. This one was setting a P0021, which says IVT Performance Bank 2. It did have some misfire codes and a rich code as well, but they were after the P0021. That's the reason the shop called me in to look at this one. Of course, we checked the oil level. That's all good. It's been changed. It's clean, just like all the rest. Our P0021 is actually almost identical to our P0011. It's just on bank 2 rather than bank 1. So similar definition as far as the code goes to the last Nissan that we were working on. This one's just on the other bank. And again, this V8 engine has dual overhead cams. Only the intake cams are phased on this one. Again, same setup as we've had for all the vehicles, but we're dealing with bank 2, which is over on the driver's side of this engine. It's conventionally mounted, meaning the front of the engine is at the front of the vehicle. And again, same definition for the code. It's the gap between target angle and the phase control angle is not where the ECM wants it to be, meaning that it's trying to phase the cam and it's not happening. It's not ending up where it wants that camshaft to be. So I verify that this does have the problem. They said it was mostly when the engine was cold, and they were very correct on that. I start this up, and cold, the engine had been sitting outside. It ran terribly. It ran very rough. I had misfires all up and down bank 2, that driver's side bank. It could barely idle. I tried revving it up, and there was actually a rev limiter in place on this one. When this code sets, this 21 code, it'll actually limit engine RPM on top of running poorly. So I had to clear the code to actually get it to rev up anymore. Once I did that, it would rev up, and once it revved up, it actually ran pretty smoothly. So that's one clue as far as to what's going on here. Again, misfires up and down on bank 2 as far as those 4 cylinders go, not on bank 1. So I know I'm dealing with one side of the engine here. Of course, that correlates to the code that I have for VVT. Another clue here, and this is particular to mass airflow sensor engines, I had opposing fuel trims to one another. So what's going on here is the airflow that's going into the engine is obviously all measured by the mass airflow sensor. So all of the air going into the engine is measured by the MAF. But once that air enters the intake manifold, it is going to be theoretically split evenly between all of the cylinders, or you could consider it between the 2 banks, right? So bank 1 and bank 2 should consume the same amount of air, meaning that the total volume of air should be divided into 2 if you look at the 2 banks. Meaning that, again, the computer's looking at the mass airflow sensor to determine fuel delivery, right? How much air went into the engine? We got to add the right amount of fuel to it. If, for some reason, the air going into bank 1 is not the same as bank 2, that mass airflow sensor total volume is going to be incorrect for both banks. So let me explain this again. Imagine air goes into the engine. We'll just make up some numbers here to make the math easy, right? Let's just say 10 grams of air go into the engine. All right, so 10 grams go in, and that's what the mass airflow sensor measures. We should see each bank of the engine consume 5 grams of air. That would be the expectation if everything's working correctly. But let's say, for some reason, I think you can tell where I'm going with this, one side of the engine was actually using less air than the other side. So let's say bank 2, because that's the one we're talking about, is moving less air through the engine. Let's say it's only moving 4 grams of air through it. And let's say the right side is moving 6 grams of air for it. Now the total measurement will still be 10, right? But instead of 5 and 5, now we have 6 and 4. But the engine computer is going to add air for 10 grams, meaning that bank 2, who should be getting 5 grams of air, is getting fuel added for 5 grams of air, but is only moving 4 through it, meaning that we're going to have a rich mixture. Now, bank 1, who's moving 6 grams of air through it, will only be getting fuel for 5 grams, meaning that's going to be running lean. Okay, so where I'm going with this is if you see opposing fuel trim numbers like this, there are other possibilities like O2 sensor plugs that are crossed or something like that, but what I'm first thinking on a mass airflow sensor vehicle, opposing fuel trims like this, that there is an engine breathing problem. Okay, so I was kind of long-winded in that explanation, but whenever I see this, I think engine breathing problem on a mass airflow sensor vehicle. And again, long story, but to go back to what we're talking about here, I've got timing codes on this engine. I got misfires up and down on bank 2. I've got rich codes on bank 2. And lean codes on the other side. The air is not moving through that side of the engine as it should. The timing is off on that bank. It is physically off. It's not something that's being imagined by the computer, perceived through a sensor. The timing's actually off on that bank. And I know that based on all these symptoms that I have without ever leaving the driver's seat, which is really handy. Okay. I know that the physical timing is off on that bank. So now my question is this a VVT problem or a base timing problem? So I want to pursue that and figure out what's going on there. So let's look at some VVT data PIDs and see what we've got going on. Now, this Infinity actually had some really useful VVT data PIDs, which a lot of modern vehicles do. They've gotten a lot better with these data PIDs. We have a desired data PID, which is where the computer wants that intake camshaft. We have an actual data PID. So using the cam and crank sensors, it's able to tell where that camshaft actually is in relation to the crankshaft. And we have a variance, which is just the difference between the two. So if you don't feel like doing the math, then you just look at the variance and see it should be at 0. They should match. Desired and actual should match. The variance should be at 0. You could see VVT actuator duty cycle as well. That was another data PID that I pulled up for this one. And you could do this for both banks. You could do this for bank 1 or bank 2. Of course, I'm zeroed in on bank 2 here to see what's going on. So as the engine's cold and it's running, I am about 30 degrees away from where the computer wants that camshaft to be. Okay, so it wants that camshaft at idle 0. It doesn't want it phased. You can see the actuators at 0. You can see the desired is at 0. You can see the actual is at 30 degrees. So we're 30 degrees off. Okay, so again, now, is this a base timing issue or is this a VVT issue, right? Is the phaser stuck in a position or did the chain jump? That's what I have to determine here. Now, going off of what the shop had told me, that this is mostly present when the engine's cold, I allow the engine to warm up while I'm watching these data PIDs. And I revved the engine a couple times as well. I actually cleared codes out at one point or another too, but as I warm up this engine, I can watch that camshaft position float closer to 0. And then all of a sudden it goes to 0. So the variance is 0, the desired is 0, the actual is 0. The engine smooths out and runs perfectly fine at idle. Okay. So now what I can eliminate essentially is a timing chain issue, because now I'm 0. I can clear the codes. They don't set at idle. My variance is 0. My timing is on, at least on that intake camshaft. That my timing is on and the engine's running fine. The fuel trim problems go away. The misfires go away. Okay, that's fantastic. So I eliminated a timing chain issue, and I haven't even left the driver's seat, which is really nice. Again, my next question is, what is the problem? Now, I was able to rev up the engine and get the VVT to activate, and it would essentially stick at times, right? So we see the desired and actual, and they should mirror each other very closely. You'd see the desired go up, the engine would attempt to phase that camshaft, and it would. You see the actual move. So the solenoid's activating, the phaser's moving, but then when you bring it back down to idle, the desires goes to 0, and we should move that camshaft back to its base position. And at times it wouldn't. It would stay advanced and then eventually float back to 0 and go. And the warmer it got, the better this got at going back. But again, when it was cold, it was basically stuck in that position all the time. So I got a pretty good feeling of what's going on here, but I do have to zero it down to this specific component. So what are my possibilities here? I think one is going to be that maybe there's a solenoid that's sticking. That's a possibility. You know, I've seen that on Toyotas before, the 3 liters, the 3.5s. I've seen it on Ford F-150s where the solenoids will stick applied and your camshaft's basically phasing all of the time, setting timing codes. Those are possibilities, but also the phaser itself could be sticking. Okay, and I've seen this on Honda Accords before, where it's just basically delayed as far as the reaction from the phaser. And I remember on Accord, I actually did this on. I had this pretty much identical problem. The data pits looked exactly the same as what's going on with this Infinity. I got it to a point where it was out of time. I shut the engine off. I ripped off the valve cover, and I could move the camshaft with a wrench. You can grab the wrench flats, and I could move that camshaft, meaning that I know that that phaser was sticking because that was not at my locked position like the computer wanted it to be. So phaser was sticking, we replaced it. Now, that's not as easy to do on these Nissans. They've got big electric motors to do the valve lift. You're not ripping that valve cover off very easily. In fact, there's not much you can do on these engines that's easy to get to. So I have to make a determination somehow. Is this a phaser? And that's my gut. My gut's telling me this is a phaser because it looks exactly like that Honda that I was referencing. But again, I want to be sure because it's going to be a big labor for them to dig into this. So the other possibility is the solenoid, right? I mentioned the solenoid stick before. And one thing I did want to mention too on the solenoids is there are different versions of solenoids, right? We have solenoids that directly control oil pressure, like all of them I've talked about so far. There are some solenoids that sit on the front of the camshaft and will just move a spool valve. That's not what I have on this Infinity, but like on a Chrysler 3.6 or a Mercedes, they call them cam magnets sometimes. But these actually physically move a spool valve in the middle of the phaser. They don't directly control oil pressure. The spool valve will control oil pressure. But the solenoids I'm dealing with here on all of these vehicles physically regulate the oil pressure to the phaser in order to release the phaser and the lock pin and get it to phase, right? There's a mechanical lock pin with a spring that gets released from the oil pressure, and then the oil pressure will change the position of the cam. It'll move the vanes inside that phaser, right? And actually one more note on that before I get back to this one. Newer vehicles I'm seeing also have what's called a park lock solenoid. And this is in addition to the VVT solenoid, right? So you'll have a VVT solenoid that'll regulate oil pressure to the phaser to phase it in a certain position. And then you'll have a separate solenoid. Again, this is newer stuff. You'll have a separate solenoid just to lock or unlock the camshaft. And it actually outlines in service information that the computer will test the operation of the lock solenoid by activating the VVT solenoid and seeing does the camshaft move when it's in the locked position. So it's testing to see is this thing actually doing its job. But that could be a failure. If that lock position solenoid fails, then all of a sudden that camshaft can move well, maybe not freely, but it'll move to a position where the computer doesn't want it to. So just keep that in mind. That's not present on my Infinity, and I don't mean to make this any more confusing than it is, but I wanted to point that out, that newer vehicles have additional solenoids beyond what we're talking about here. But I'm kind of zeroing in on my solenoid here because I'm thinking I can probably test my solenoid on this Infinity easier than I can the phaser. At least eliminate it as a possibility. Now, I go out to the engine bay, and unfortunately, it's not so easy to remove these solenoids. That was going to be my first thing, is pull a solenoid and see, is this thing sticking, something happening with it. It's like a 2-hour job as far as the book time goes to yank these solenoids, and that was not something I was going to do out in the parking lot here. So I still have to try to make a determination here. So what I decided to do was to scope both the voltage and the amperage going to both solenoids, right? So we have a bank 1 and a bank 2. I'm going to verify that the solenoid's not only getting amperage when it should and not getting amperage when it shouldn't, but you can actually see physical movement in a lot of solenoids based off of these waveforms. Not everything. Sometimes it's easier said than done, and some solenoid patterns just don't reflect physical movement as easy as others. But what I'm hoping to do is compare bank 1 to bank 2, since I don't have any problems on bank 1, and I should see a similar pattern. I should see an exact same pattern between the two. If I see a difference on bank 2, then I'll consider, okay, maybe this solenoid is at fault here. Well, I do this. I look at the amperage waveform as the solenoid's opening and closing. I look at the voltage waveform as it's opening and closing. They do look identical. Now, I can't say for sure that I can see pintle movement in these waveforms. It's a little tough, but they look identical. I don't see a difference between the two. And I'm kind of stuck at this point because there is still a potential, even though my gut's telling me phaser on this one, there's still a potential that this solenoid could be bleeding pressure past it and keeping that phaser, out of position longer than when it's supposed to be. Or the phaser could be stuck. I'm really down to those two components. So at this point, again, I'm not going to spend 2 hours to pull this solenoid. I tell the shop exactly where I'm at. I show them my findings, look at the scan data, look at the scope pattern. Here's what I got. I know it's one of these two components for sure, but you're going to have to do some, manual labor to get these components apart. And I told them, I was like, if you want, you could either swap these solenoids or put a new solenoid in just to verify that the problem is still present. And if it is, you're going to be tearing this thing apart to get to the phaser. It's up to you. And I told him, I was like, my gut is telling me that it is a phaser, but I'm kind of up against it here unless you're able to remove that solenoid. If you want to remove it, call me back. I'll come check it out. They elected to just put a solenoid in it because they're pretty good at, again, a mechanical repair. Didn't take them very long. They popped a solenoid in there, exact same problem. So at that point, we know it's the phaser. That's the direction that we're going. They put a phaser in it, and that was a big teardown on this engine. Problem was gone. So the phaser was internally sticking. That's where the issue was with this vehicle. Okay, so that's going to do it for VVT. Hopefully you learned something from that, enjoyed those case studies. But other than that, thank you for listening, and let's all get out there, start fixing the world one car at a time.